Play with magnets as a kid was pretty simple. You had a north face and a south face, and they would align and slap together. But now, something else is happening. We're at a company called Polymagnet here in Alabama, and if you look at their design, you gotta get an idea of what they're doing. They can print specific magnetic designs on the surface of a magnet. Now, you've never seen anything like this because it's bizarre. You can get new, unique, crazy behaviors just by manipulating that magnetic field. Let's go check it out.
This is Jason Morgan, head of engineering. He's agreed to teach me about polymagnets and show me some stuff that most people don't get to see.
So this is a conventional magnet.
Okay.
So if you look at the conventional magnet, it's magnetic.
Wait, hold on, what is this?
This is magnetic viewing film.
Magnetic viewing film.
Yes.
Okay.
What that does, it shows you transition in the magnetic field.
Uh-huh.
So it allows us to see where the magnetic field transitions from north to south.
Got it. Okay.
So this is a conventional magnet. It's a neodymium magnet. So north face, got a north face and a south face. And the magnetic field goes from one face around to the other face.
Can we draw on the whiteboard?
Absolutely.
Let's say this is our magnet here.
Right.
So the field lines are going to go out and in, right?
Go ahead, Jim.
Yeah, you'll have, closed loop, don't want to break Maxwell equations, all the way around from your North Pole to your South Pole by convention.
Gotcha. Okay.
So what we do different is we take a magnet and create hole regions on the surface. So we create north and south on the same surface of the magnet. And what that allows us to do is close that circuit that David was talking about in a much more compact space. And that gives us a stronger field close to the magnet, a stronger force close to
Okay, so I think I got it. So what you're saying is, if we've got the big loop here,
Yes.
north and south, you're doing the same thing, only they're looping much closer together.
Correct.
Like that? Even in on itself.
Almost, right. So what actually happens is you have the north and the south on one face of the magnet. And so what happens is you have the field go like this. And so instead of this long field that can create interference and waste energy, you have a tight field so that it's tightly controlled, and you have the force really focused near the magnet.
These people are like modern day wizards. They can create whatever magnetic field they want on any of these magnets. I sat and talked with them for about an hour and came to understand that the way the magnet interacts with the target material determines how strong it's attached.
And so what you're saying is the magnetic field in this one is going to come up and around and go all the way back to the back of the magnet, correct?
Correct.
Okay, in this one, we have a tighter grouping of the magnetic field, so the circuits are going through the steel and they're completing just outside of the steel on the other side, correct?
On the same face of the magnet.
Same face of the magnet, so they're not going all the way back around to the back side.
The same way.
Gotcha. Here I have a very dense spacing of magnetic fields, and so they're all completing inside the steel.
Inside the steel, correct.
Do I understand magnets?
You do.
Excellent.
You understand polymagnets.
Polymagnets.
Let's say you have a piece of steel that's a certain thickness and you want to attach this 1-inch magnet to it. Engineers first design and print the magnetic field and then put both the magnet and the steel into this pull test machine to quantify the exact force versus distance curve. If they want to, they can then change the magnetic field and tailor it until they get the exact force curve they're looking for. This ability to manipulate the strength of the magnetic field coupled with a really clever geometry allows you to create fascinating magnetic behaviors. For example, these magnets, they're attracted to each other, but they don't touch. They stop just a few millimeters away and seem to hover. This behavior is what they call a spring.
These are springs.
Uh-huh.
All right, this is a spring that's a little bit different. It's a little more complex and can be used as a latch. So you see that it acts as a spring. So if you think about it, let's say like a cabinet door closure. You could have a cabinet door that came together in a kind of soft close with some shock absorption, but then you could twist it to latch and it holds strong.
No way. So I can pull against you like
Sure.
that. I close it, and then when I turn it,
Locks into place.
that's ridiculous.
Time out. This is way different in your hands than it is on a video. Attraction and repulsion in the same axis, and then you rotate and you can't pull it apart. Now we know that any sufficiently mature technology looks like magic until you understand exactly how it works. Watch the faces of my highly educated engineering coworkers as I put this in their hands.
What's going on there?
I'm not really sure.
That is weird. How does that work?
Ooh, it catches. I have no clue.
So if it's not magic, how does it work?
You have that locking point where it holds tightly, but then you turn past the descent and it will hold in that spring location.
That's genius. That's going to change doorknobs. I really think it is. Are you excited about that?
We like this one a lot.
Jason agreed to let David show me some of the special machines in the back that they invented to program magnets. They look just like 3D printers, only you load a blank magnet and it can create whatever magnetic field you can imagine. While we waited the 5 or so minutes it takes for these things to run, I went back out and met more magnet geeks and tried to learn more lingo.
You said a maxle?
A maxle.
A maxle is a what?
It's a magnetic pixel.
Really?
Yeah.
And so a magnetic pixel would be a node inside the magnet that's printed. So the image that you just printed is created by magnetic pixels or maxles.
More or less.
Can we go look at it?
Oh yeah.
Think about these maxles. Somehow this machine creates north and south polarized maxles inside the magnet. You can add these pixels up to basically make images that can create forces. If you couple one image with a complementary image, you can then create incredible three-dimensional behaviors. This technology is so new, there hasn't even been enough time to think through all the different applications. I think it's a game changer. I'd love to hear what you think in the comments, and please consider passing this video along to all your smart friends to see what they think.
So this is the Smarter Everyday magnet.
Yeah, so
Oh man. So you could make a marble track. Could you do that?
give me big enough magnets.
This is bizarre. All right, so here we go. Smarter Every Day. We have a marble, and it follows the field lines.
So there you go. The entire foundation of magnetic circuit design technology just changed. And I'm not gonna lie, it makes me look at magnets just like I did when I was a little kid.